Greetings and welcome, ladies and gentlemen. Today we're going to talk about matrices, which are really, they're just a way of arranging information when we have a lot of it into some sort of rows and columns. So I mean, you could take like a real world problem. Let's say I have types of ice cream, and let's say you've got like, I don't know, vanilla, chocolate, and swirl, right? And then you have like, I don't know, maybe types of cones, right? And maybe you've got the like sugar cone, and then like you've got the waffle cone, right? And if I wanted to like arrange some of this into some sort of arrangement, I guess, I could actually put them into kind of rows and columns where maybe in one direction I could have ice cream, and in the other direction I could have the cones, and with matrices we'll put these little brackets around it. So let's see, so I could have sugar, vanilla. Let's see, should I do it that way? No, I guess I'll do vanilla sugar, vanilla waffle, right? And then we could have chocolate sugar, chocolate waffle, and then we could have like, I don't know, swirl sugar. I guess the double S is confusing. And the swirl waffle, right? And I could just arrange that information, right? So that's kind of what a matrix is trying to do, is arrange things like that. Now, in this case, all of these ended up being kind of, you know, sugar cones, and all of these ended up being waffle cones and stuff. But that doesn't have to be the case in a matrix. You could have all sorts of different things held within them. Really, a matrix, it's kind of combining a spreadsheet and math, which, I mean, really are some of my favorite things. So, yeah, of course I love matrices. Matrices, by the way, is plural for matrix. So it's a matrix for a singular amount of them. Like the movie, yeah. In the movie The Matrix, you saw like the zeros and ones like scrolling down, right? That was essentially the matrix that was storing the data of the entire universe that they'd made in the computer system. Yeah, hence they called it the matrix. So matrices is plural. Sometimes I intentionally mispronounce it as matrices just because I find that amusing, but don't go believing that that's the right way to say it. Because someday, you'll be in college someday, or you'll be president of the United States someday, and then like, I don't know, you'll drop that word and you'll look like a fool in front of everybody. But yeah, so I mean, I could typically will be using matrices to store values of numbers, or maybe even variables and terms and stuff like that, expressions. One of the things I want to point out is that matrices are actually not separated by commas, which I would love it if they were, but they're not. It's like, all right, I guess you can do that. So let's say I've got a matrix, and matrices, by the way, are usually denoted by capital letters that represent them. So let's say I have the matrix 1, negative, I guess you can't have negative 0, can you? It's not a very helpful number. And then 3, and then we'll have a half, and 0, and 4. Okay, so here's my matrix A. All right, and there's a couple different things you can pull from this matrix. One of them is you can know what the size of the matrix is. All right, which is the rows cross the columns. So in the case of this matrix, this is how many rows are there? There's 2. And how many columns are there? 3. Okay? So it's always rows by columns, like so cross little by, like a 2x4 that you might buy. That's what that little symbol means. So I'm not multiplying those, although I guess if you did multiply those, it would give you the number of elements within the matrix, which is the next thing. So elements are the individual numbers, terms, or expressions within the matrix. You're using these or mine? Mine. Well, some of mine do too. They're pretty close. Right. So this matrix has 6 elements within it, and there's actually ways to denote which element that I'm referring to. The matrices elephants. You could look at A11. Would be referring to the first row and the first column. So A11, the first row is this one, the first column is this one, so the intersection between those two would be the 1 there. Okay? A23, and I find this really annoying that these aren't separated by commas. Like, what? Come on. Like, just give me a little comma there. 2, 3. I'd love it. Because what happens if I have a matrix that's like got a whole bunch of rows and columns, and then I'm referring to like matrix B, like 2, 1, 7, and is that row 2, column 17? Is it row 21, column 7? Like, what does that even mean? I don't know. But let's see. So A23, or no, A23, right, would be the second row, third column. So that would be the element that's the 4, correct, right? Because it's the second column, 1, 2, 3, second row. So the intersection, bam, crosshairs. Did I? Whatever. So rows and then columns. The way you remember columns is columns are vertical, just like in some sort of Greek structure, right? So what would A21 be in this particular matrix? So second row, first column, 1/2. I agree. And one of the challenges, like I notice how I've been kind of like putting these little tick marks for the rows and columns when I notice where things are, because oftentimes people think of kind of the coordinate system and they think over 2, down 1, or something like that, and that's not going to give you the right spot. How would you denote which element is -7? Yeah, first row, second column, so that's A12 would be -7. All right, so just so you're aware, that's kind of how those things work out. And like I said, matrices don't have to just hold numbers. I could have like a 1x and a 2x plus 4 or something like that. So like you can't actually have them containing different things if we wanted, and that can be helpful for us as well. So let's see. So we know the size of the matrix. We know the number of elements. Let's see. One of the things I'd want to point out is a square matrix. I think you guys could guess. Is size, I guess I'll word it this way, n by n, right? So that would be like a 0, 1, 2, 3, or a 1, 1, 1, 1, 0, 0, 0, 0, 2, 2, 2, 2, pi, e, I. And let's do X. There we go. So what's the size of this first matrix? I guess I could call this matrix B, and this is matrix C. What's the size of matrix B? The square is the shape, but what's the size? 2 by 2. And the size of matrix C would be 4 by 4. Right? So it's always rows and then columns. Right? RC, remote control. Actually, the other thing that I use to remember the rows and then columns, I usually think of roll call, right? Like if I was calling off a list of students to determine who's present, which I did take attendance today, I'm quite certain. Right? So row, column, am I right? Yeah. Let's see, some other facts. A zero matrix would be all elements are 0. Right? So actually here's a 1 by 1 matrix. Not very interesting. So I could refer to this as the 2 by 2 zero matrix if you wanted. And actually I believe these are sometimes denoted by the, it looks like the letter O, I suppose, but it's kind of like a 0, so you might refer to that as that. So let's talk about adding matrices. Matrices. So let's see. So a couple prerequisites. Well, I guess there's really just one prerequisite. Is the matrices must be the same size. Okay, so that's key. And in order to add, you add the corresponding elements. Which is perhaps what you would assume. So what we could do is, let's say I've got the matrix 2 and -7, and I'm going to add that to the matrix 0 and 5. The result of this addition, all right, I'm going to write an intermediate step here that normally you probably won't have to write. So what's the size of my answer matrix going to be, you think? Well, what size is this? No? Rows, columns, so 2 by 1 plus a 2 by 1 is going to equal a 2 by 1. So what is element 1, 1, you think, going to be made up of in this? Yeah, it's going to be composed of the 2 plus the 0, and element 2, 1 is going to be the -7 plus the 5. And like I said, you wouldn't normally write this step. I think you could do it in your head. But eventually, you might have some steps to write. So 2, -2 is my matrix. Actually, my first year teaching, I taught on matrices, and well, related to graph theory. And we ended up having matrices that were like 5 by 5 matrices, right? And every element within them was either a 0 or a 1. And I didn't have a good way of like giving the students the answers, so I had to read them off. And like reading the answers for like 3 minutes, I was just like 1, 1, 0, 1, 0, 0, 1, and I was just like speaking binary is what it felt like, and I was quite amused at it. And I don't think I was able to keep a straight face very well. I just like started laughing, and the kids were like, "Really, Mr. Like, it's not that funny." Like, but I was just like, "I can't even read these anymore. I find it hilarious." But anyways, so adding matrices, that makes sense. If two matrices are equal, equal matrices? Well, it's probably as you assume. They're the same. First of all, must be the same size, and their corresponding elements must be equal. So that's what equality means in the world of matrices. So I guess I could do a little example of that if I wanted. X 2y 4 equals, let's do 7, -8, and, oh, no commas now. And we'll do 1/2 z. So, if these two matrices are equal, then what must be true? What else do you know? X equals 7. Yep. Right, and then if I wanted you to actually find out what these variables were, you could divide by 2 here, you could multiply by 2 here, and you could end up getting y equals -4 and z equals 8, right? So I just want to point out, right, so these matrices had to be the same size. What size are these matrices? 1 by 3, right? So I'm glad you guys hesitate. Like, I always double check myself with matrices because it's real easy to be like, oh, those are 3 by 1. But no. Let's see. Let's see. So we've talked about adding. Let's talk about scalar multiplication. Okay. A scalar is a single number, not a matrix. All right. And scalar multiplication, basically what I'll do is multiply every element within the matrix by the number, or by the scalar. So what we've got here is, we'll do a little example. So suppose I've got this. Let's say I've got 3 times this matrix. 2, 1, -1, 3, and 5, and -4. So in order to do this, this is essentially kind of like the distributive property. I'm just going to, right? Everybody gets multiplied by the scalar. So this guy's called the scalar right there. So what size is this matrix, by the way? 3 by 2, because 1, 2, 3 rows, right? Let's see. So let me see if I can be sneaky. What will 3 times A22 be in this? Yep, because element A22 is this guy right here. Second row, second column, right? Second row, second column. And 3 times that is 9. What would 3 times A, yeah, I guess I didn't label this matrix A, but you guys caught on. What would 3 times A21 be? Because second row, first column, right? So that's why I'm doing this, and I'm not trying to be facetious or anything. I actually know it takes this long to really understand. Like, okay, rows, columns. You'd be surprised, right? Because you'd be tempted to be like, oh, it's the number of elements within a column, but don't get thrown off by that. So let's see, and let's actually figure out what this is. Right, so in order to do this, you wouldn't normally write this step, but that'd be 3 times 2, 3 times 1, 3 times -1, 3 times 3, and 3 times 5, and 3 times -4, right? So that would be my kind of work step, but like I said, I don't require you to write that. So we'd have 6, 3, -3, 9, 15, and -12. And it looks like I forgot my little closed parenthesis there. Now, so I just want to point out, like, kind of spacing things out in a matrix is important, especially since we don't have commas separating our terms. Okay? And also, I want to point out that these little parts of the square bracket are significant, because later on we will actually have what appears to be the absolute value of a matrix. Actually, it won't exist in this case. It'll only work on square matrices. But so the notation, the way we write this, does matter. So I think we're good. Oh, I just knocked something over, but that's okay. I think we're good to go. So yeah, matrices, elements, sizes, scalar multiplication, addition. And I guess I could also tell you that, well, maybe one more side fact is that the zero matrix is also the additive identity. And we'll talk more about identities later on. And what I mean by that is that the zero matrix is the thing I could add. Actually, I happen to have all square zero matrices here. Is the thing I could add to any matrix to not change it. All right, that's what an identity is. But like I said, we'll actually do some more identity work a little bit later. But okay, all right, thanks, internet friends. Bye-bye.